Alright, section 1.3 is what we're going to be working on now. And we're still going to be dealing with limits, but like with the previous lesson, we had looked at finding limits numerically, like with the table, and then also by looking at the graphs graphically. So now we're going to go to that third way of finding limits, which I told you was analytically. Now there's one theorem that's listed in your textbook. They refer to it as Theorem 1.1. Now with the B and the C, they're just telling you that B and C are just representing numbers. Alright, so you got your limit notation. So if you have the limit as x approaches c, so again they're just using that lowercase c to represent some number. So the limit as x approaches c of b. Now b is also just a number based on this. Okay, so you've got a number here and you've got a number here. So if you notice, what the limit is equal to is exactly the same as what you have here. So the example that I have here at the bottom shows you this. So I just chose x equal 4 here. So you got the limit as x approaches 4 of 9, then your answer is going to be just 9. So anytime your function is just a constant, then that limit is going to be just that constant. It's not going to matter what it's approaching at all. And the reason why is if you were to graph this function, it's actually just a horizontal line. So I'll just do a rough sketch here real quick. So if you were to graph the function, of course this being your x-axis, this being your y-axis, so of course up here somewhere would be, your value of 9. So if you were to graph this horizontal line, now you're looking at this as x approaches 4, so 4 would, be along here somewhere. So if you go up, locate that here on your graph, see if you approach from the right hand side and you approach from the left hand side, the y value that you're approaching each time is still going to be 9. Even if I came down here and I said, okay, well let's do as x approaches 8. Same thing. If I look at it from the right side, look at it from the left side, the y value is still 9. But your y value never changes from 9 when you have a horizontal line. So just remember, anytime that you're asked to do the limit of a constant, then that limit is just whatever this constant is. Alright, the limit can be evaluated by direct substitution if the function is defined or it exists at this number c. So of course direct substitution just means that you directly take the value that you're approaching and substitute it into the function. Again, it can be done that way as long as your function is defined. Now, so one of the main ways that we saw a function wasn't defined in the earlier section or the previous section, remember, it's like where we had an open circle on our graph, our function wasn't defined there. Like in that case, you couldn't do direct substitution, but if you can, that's the quickest and that's the easiest. So like when you approach all of your homework problems in this section, you should always just approach it with, okay, let's try direct substitution and see what happens. Alright, so here's the first example. Limit as x approaches 1 of 3x cubed minus 2x squared plus 4. So like I said, just start all these off by do direct substitution, see what happens. Okay? So when I do direct substitution, then I would have, of course, 3 times 1 cubed minus 2 times 1 squared plus 4. Of course, you can use your calculator to help you do the calculations there, but that's just going to be 3 minus 2 plus 4, so that's going to give me a value, excuse me, of 5. So that would be your limit. Okay? Like I said, direct substitution is easy. Always try that first. Alright, second example. again, take this one, try direct substitution, see what happens. Okay, so that means I would have the square root of 3 plus 1 divided by 3 minus 4. So, of course, this is square root of 4, but square root of 4 then would give me 2. And, of course, 3 minus 4 is negative 1, so that means that your limit is negative 2. Now, you could always, I'm not going to take time, but you could always like graph this function in your calculator, you know, and locate the x equal 3 and just see if at x equal 3, the y value that your graph is approaching from both sides is negative 2. So you can always go back and look at it graphically like we were doing in the previous section. Alright, still dealing with direct substitution, but looking at some trig functions. And trig with your values may be something that you need to kind of freshen up on a little bit. Okay, so on this one I have the limit as x approaches pi of tangent x. So my number, my value that I'm approaching is pi. So again, direct substitution means that I would have tangent of pi. Now, you actually can put this one in your calculator. You would need to make sure that you're in radian mode. You know, since your value is pi, that would indicate radian mode. But, let's see, tangent at pi, of course, you could also figure it out other ways. You could figure it out, of course, pi is the same thing as 180 degrees. So, like, for instance, let's see. Okay, so tangent of pi is going to give me a value of 0. Okay, I'm going to give you some more information separate from this video with your trig, like some refresher stuff. Okay, but like I said, you can just put that in your calculator. You would have to make sure, again, you're in radian mode. So you just type in tangent pi, it equals, you get 0. Alright, number 4. If I do direct substitution here, I've got to plug 1 in. So I would have sine, of course, of pi times 1 over 2. Of course, that's just the same thing. Of course, pi times 1 is just pi. So sine of pi over 2. Of course, pi over 2 is the same thing as 90 degrees. Again, you could put it in your calculator. Of course, this may be one of the values, or this is one of the values that you would have memorized. So if you remember that, sine of 90 degrees or sine of pi over 2 is actually positive 1. Okay, number 5, again, direct substitution. So we would have cosine of 3 pi. Okay, now if you remember what your cosine graph looks like, of course, when you learned your graphs, you only learned your graphs out to 2 pi. You know, so you could extend your graph if you wanted. Again, you could just substitute this into your calculator. Again, you would, once you've changed it to radian mode, it'll still be in radian mode, but that would give you, let's say, cosine of 3 pi would give you a value of negative 1. Alright, number 6. Again, direct substitution, so I would have cosine of 5 pi over 3. Now, this is going to be one, like if you rely on your calculator, you may end up getting, you know, a big long string of decimal places. Sometimes you do, sometimes you don't. Now, this one works out where you don't. If you plug it in, it actually tells you 0.5, which would be the same thing as 1/2. But if you remember, you can have values like square root 3 over 2 or square root 2 over 2. And in that case, you would have to go back and do some figuring by hand. Like, I don't want you to give me a decimal approximation on these. What you would need to remember about this problem is, first of all, reference angle. Of course, reference angle for this would be pi over 3, which is the same thing as 60 degrees. Now, if you do 5 times 60, that's going to give me 300, which means, 5 pi over 3 is 300 degrees, but the pi over 3 is just your reference angle, and 300 degrees is in the fourth quadrant, and cosine is going to be positive in the fourth quadrant. Okay, so if you recall from your table, cosine 60 degrees, again using your reference angle, cosine 60 degrees is 1/2, so that's where the 1/2 comes from, but you would keep this positive because of the fact that cosine's positive in the fourth quadrant.